Welcome to my video lecture based on electric circuit theory. Paper code ECEE301. Today's topic is based on numerical on magnetic coupled circuit. This lecture is continuation with previous lectures dependent on the module of magnetic coupled circuit. In my previous lectures, I have discussed about magnetic coupled circuit and the basic needs of magnetic coupled circuit and what is dot convention and how this dot convention can be implemented in case of a circuit. That is I have highlighted in my previous lecture. Myself, Urmil Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandra Institute of Technology and Sports Complex. Previously, this institute is known as Dr. Sudhir Chandra Degree Engineering College, and this institute is under JIS Group. This lecture will mainly give on the numericals of magnetically coupled circuit. So basically, magnetically coupled circuit means basically electricity and magnetic phenomenon, they are just adjacent with each other. Where there is electricity, there will be magnetic field also. So those magnetic fields have some effects on electrical circuits, and due to that effect, a magnetic circuit or magnetic field basically coupled with the electrical circuit phenomena. And the main effect of magnetic coupling is mutual induction and self-induction. And due to that, self-induced EMF and mutually induced EMF is created. And EMF means voltage. That means this voltage will be addition with our actual supply voltage, and this drops will be there. And from the dot convention, we have known that position of dots dependent upon that mutually induced EMF is positive direction or negative direction. So based on that, some numericals has been solved in my previous lecture, and in this lecture we will do some theory first and then we will go to the numerical calculations. Let us start with the magnetically coupled circuit. So for doing the numericals, we have to understand some basic circuit phenomena or basic transformation for easier calculation of a circuit. So among that, this topic is related. That is determination of equivalent T and pi circuit of linear transformer. Conductively equivalent circuit of a magnetic coupled circuit. Here we will make it equivalent of T and pi circuit. This is the circuit of a linear transformer structure. Okay. And here the mutual induction is happening in between and the dots are present in the same position. That means the mutually induced EMF will be positive side. So we are applying KVL for the two meshes. First mesh is this one. This is number 1 mesh. And this one is the second. So applying KVL in the first mesh, we are getting that L didt, that is self-induced EMF, plus M dit dt, the mutually induced EMF due to the current of adjacent coil I2, which is flowing current through the adjacent coil. So our equation becomes E1 equals to L di1 dt plus M di2. Similar way, if we apply KVL for our second loop, our equation will be V2 equals to M di1 dt, because mutually induced EMF will be created because of the current of the adjacent coil, that is I1, plus into di2 dt. So putting in place of L1, we are putting j omega L1 into I1. In case of M, we are putting j omega M into I2. So taking common j omega, we are getting L1 minus M into I plus j omega. Taking j omega M common, we are getting I1 plus I2. Similar way, we are getting these two equations, V of V1 and V2. Now we will want to convert it into T circuit. So for making a T circuit, we have taken the two equations of V1 and V2. We have taken these two equations, this one and this one, and we have written it here. Now therefore the equivalent T network of the linear transformer is shown here, where we have quoted the formation of T, and here this is the mutual coupled branch which is related with both loops, and this is the branch inductance where it is connected with current I1, this one, and this is the branch where it is connected with the current I2. So we have put these two and it will have formed the T equivalence of the transformer circuit. Now we will do the same thing for pi circuit. We are making the same equivalent transformer circuit to pi form, and we are getting that it will be like two parallel combinations where V1 is the input voltage and V2 is the output voltage, and this is the inductance LA, and this is the inductance LC, and this is another inductance LA or LD, whatever denotion you are using. So that is the pi formation of the same nature. So here, using the concept of T and pi conversion or star delta conversion, we get the equivalence of pi circuit of a linear transformer are as follows. Three inductances LA, LB and LC we have taken, and those value of those LA, LB and LC are just like this. We have used the concept of star delta conversion here, basically, nothing more than that. Here also, if any dot changes its location of the winding, the sign of M will change and hence the inductance's value will be also changed. That we have already studied in our previous lecture, that when the dots position are changing, then the direction of current or direction of sign of mutually induced EMF is changed to positive to negative, like that. So let us now consider some numerical problem related to coupled circuit. So let us consider, find the effective value of inductance for the following connections. Here our first combination, we are seeing that there are two inductors, one value is 5 Henry and second one is 10 Henry, and in both cases dots are placed in the entering position, that means same position dots are present. Same position means the mutually induced EMF value will be positive. So the equivalence of this series adding connection will be L1 plus L2 plus 2N, this formula, and putting this value we are getting that the total effective inductance is 19 Henry. Now let us consider the second problem where two inductances are given, one is 2 Henry and another one is 4 Henry, but the dot positions are in opposite. first case entering and second case it is positioning leaving. That means our mutual inductance will be negative for this case. So this is a series opposing connection. So our effective inductance will be L1 plus L2 minus 1 and our result value will be 4. In a third case, we have 3 inductances. In these 3 inductances, we can see that they are all positioning entering position. But here the mutual inductance will be affected between the 3 combinations. So effective inductance of first coil, it will be L1 self-induced EMF, then mutually induced EMF will be affected for 2 another inductance. That one is for M12 and M13. And both will be positive because the dots are in all cases it is in entering position. Next, second effective inductance for coil 2, it will be L2 plus mutually induced EMF for first coil, that is M12, and for second coil M23. All will be positive. And effective inductance for the third coil, it will be L3 plus M13 plus M2, and this is the effective inductances in the individual coils. Now, summing all these values, we are getting the total effective inductance here, and that value is 800. So in that way, you can calculate the series inductance combination and the effective inductance. Now let us consider another problem. For the circuit shown in the figure, if L1 equals to 0.4 Henry, L2 equals to 2.5 Henry, K equals to 0.6 and I1 equals to 4I2. That is equals to 20 cos 500 T minus 20 degree mm. Evaluate the following quantities at T equals to 0. Now we have to calculate at I2, next the value of V1 and the total energy stored in the system. So let us consider the values of I1 and I2. So the value of I1 and I2 will be I1 equals to 20 cos 500 T minus 20, and the value of I2 will be divided by 4, because in the question it is given 4I2 equals to this, that means the value of I2 will be 4 divided by 4. So we are getting that I2 equals to 5 cos 500T minus 20. Next we have to calculate the value of V1. Okay, before going to V1 we have to calculate the value of I2 at T equals to 0. So we are putting the value of T equals to 0 here, and we are getting the value of I2 equals to 5 cos minus 20 degree, that is 4.7 milliampere. Now for second problem we have to calculate the value of V1. So by calculating this value, we have to calculate this problem using with help of mutual inductance. So first we will calculate the value of M, that is from well-known formula, that is K into root over L1 input. From there we have calculated the value of M, that is 0.6. Now we know the effect of mutual inductance, and here it will be V1 equals to L di1 dt plus M di2 dt, because for first circuit the effect of mutual inductance will be for the second time. So it will be M di2 dt. So putting all these values, we are getting that B13 equals to minus 500, 5500 sine 500t minus 20. Now again we will put t equals to 0 for the given problem, and we are getting the value of B1 is 1.881 B. Now in third question, we have to calculate the total energy stored in the system. So for calculating this value, we know that energy stored by an inductor equals to half Li square. So for this problem, it will be half L1 I1 square plus half L2 I2 square plus m I1 I2. So putting all this value, we are getting that energy equals to 161.32 microjoule. Now again the same thing comes when at t equals to 0.5. We have to calculate the value of the energy stored in the system. So putting this value, we are getting that the I1 value is 4.5 ampere, and putting this, we are getting our total energy is equal to 16.875 Joule. Next, we are coming to our next problem, that is write the loop equations for circuit shown in the figure. We apply the dot convention for the circuit and getting KVL equation for the three meshes. So for first mesh, we have an inductor, and that is related with the second loop also. So the mutual inductance of this first coil will have two effects, for I2 current and another for I3 current. So we are getting this equation, KVL equation from the loop 1. Similar way, we have calculated the KVL equation for loop 2 also, and same way we have calculated the KVL equation for loop 3. This we have to remember that for first loop, the mutual inductance effect will be for M12 and M13. For second loop, it will be for M21 and M23, and also for M12 and M13. For third loop, it will be M23, M12, M31, M21. These four methods will be there. Next problem. For the circuit shown in the figure, determine the phase share currents of I1 and I2. So for solving this one, we have formed again the KVL loops, mesh loops. So applying KVL, we are getting these equations here. Here the mutual inductance is shown. This is current entering, and here current leaving. That means the mutual inductance effect will be minus. Okay. So the mutual inductance effect here is considered as minus J6I4. So in similar way, we have calculated the KVL equation for loop 2 also, or mesh 2 also, and using Cramer's rule, we have solved this problem. And the value of current we are getting this one. So that is the solution of the problem, where we have to determine the phase currents of I1 and I2. Here we have converted this values with help of Cramer's rule. You can use any other rules also. So whatever you feel easy, you can apply that also. So not much more today. I have solved different problems with problems related to mutually coupled circuits, and the main concept here is the dot convention, and with help of dot convention we can solve different kinds of numerical problems, and here the main thing we have to use, that is KVL. Okay, still. But the factor is dot convention. You have to understand the mutual induced EMF will be positive or negative, and these values you need to consider. Nothing else. Only that much is sufficient for solving these problems related to mutual induced, mutually coupled circuits. So thank you all. Thank you all for listening my lecture. And this total lecture I have taken the notes from the book of Omji Chakraborty of Circuit Theory. You can follow that book, or you can follow the book of B.Y. Choudhury also, or the book of Surajit Bakshi. Whatever book you will follow, whatever you feel that is easy, you can follow that book. But I will prefer that you can must go through the book of Omji Chakraborty in this paper, because that books have lots of numerical problem solutions, and this is very, very effective. Thank you all. Thank you all for listening to it.